working at the intersection between nuclear theory and quantum information theory. And she really has been, I think, leading the charge to understanding how exactly we would do things such as simulate lattice quantum field theories on quantum computers. And today, Zohreh's going to be telling us about quantum simulation.
Thank you very much for the very nice introduction. I appreciate it. All right, so yeah, it's a pleasure to be here. My first time at the campus of University of Toronto. It's a pleasure. I'm happy to talk about some of my research. Again, I had a hard time picking the topic. Maybe that's the problem with kind of my research. It's all over the place. So I've been focusing a lot on theoretical aspects of a program at the intersection of nuclear and particle physics and quantum information science. But I've been also working a lot with experimentalists on making some of these proposals reality on the hardware. I've been also thinking about algorithmic side of things and the kind of things that my computer science friends would like to investigate. So it was kind of a hard choice to how to kind of pick the topic here. Then I decided to talk about some of the things that were most recent. So I'm more excited about that, and primarily because I wanted to make some new slides. I was kind of tired of my older slides, so we'll see. So what I'm going to talk about is a topic that is actually becoming quite hot in nuclear and particle physics: how to simulate scattering processes using quantum computers. Scattering is a very important physical process. It has allowed us to learn about subatomic particles, all the underlying interactions. And for many, many decades, it has really guided both theory and experiment in where to go and how to find new physics. And even today, we're building multi-billion-dollar experiments to collide particles and learn new stuff. So is it possible to simulate hadronic scattering? And I tell you what the hadron is, using quantum computers. If we can do that, maybe we don't have to build multi-billion-dollar experiments. Maybe we just build our quantum computers and quantum simulators and do that. Well, of course, that's a dream, but even if we want to learn something to interpret the result of these multi-billion-dollar experiments, that would be already great. So that's sort of the plan. So that's why I thought, let's talk about hadronic scattering. It's really a hot topic at the moment. So what I'm going to talk about is how to approach this problem, starting from very simple theories all the way to making our way into gauge theories of nature, gauge theories of a standard model of particle physics. And that's sort of the ultimate goal. Okay, so, but we have to build the steps towards it. So let me see if it works. Now it works, but I think I should be closer to this. Okay, so my talk is going to have 4 parts, but most likely 3 parts, because I gave this talk yesterday at another institute, and I realized that I could manage only 70% of my talk. So let me tell you what they are, and maybe we can just skip one of the topics depending on what the preference of the audience is. Obviously, we'll talk about background and motivation of this research quickly. Then I'm going to talk about part 1, which is studying confinement and scattering already in spin systems. These are the systems that are pretty easy for the current or present time analog quantum simulators, but also digital quantum computers. There's a huge community out there that is sort of investigating spin Hamiltonian and spin models. Can we do like a scattering processes with the spin models? The answer is yes, and I'm going to tell you about that. Part 2, I'm going to then start thinking about gauge theories, because these are the fundamental theories of the standard model. These are eventually the kind of the theories that we would like to start with to really study particle collisions in actual experiments. So I'm going to talk about an abelian gauge theory in 1+1 dimension, how we can do a scattering by using sort of an analog quantum simulation. But don't worry, if you don't like analog simulators, I'm going to talk about how to approach the same problem using digital universal quantum computers, how to build efficient algorithms to study problems like this. So let's decide. Which one should I skip? 2. 2. All right. Okay, I'll skip 2. So I'll talk about 1 for those of you who are interested in spin systems, and then I go straight to algorithms. Okay. Although it wasn't a democratic decision, it was just like you two, like, okay. So let's talk about why we care about these kind of problems. Okay, so this is sort of the overarching goal of our programs. My background is in nuclear particle physics, as Nathan mentioned. I've been doing a lot of both theory and classical computations of particle physics to understand how particle physics can sort of lead us to nuclear physics, which is a bit more complex in my view. And because it was very hard to do those kind of simulations, I started to think about quantum simulation. So what are we trying to do, essentially? This is sort of the roadmap for simulation for nuclear and particle physicists. We have an underlying theory. It's a standard model. It's very neat, beautiful, rigorous theoretical framework that describes quantum mechanical and relativistic interactions in nature, strong and electroweak interactions, unfortunately not gravity yet, but still it's a pretty complete picture. And the idea is that we start first principles from interactions in the standard model based on quarks and gluons and leptons and everything else, and be able to predict complexities in the visible sector of the universe. For example, we would like to understand the phases and evolution of these phases after the Big Bang in early universe. And the same kind of thing happens in heavy ion colliders. Or in particle colliders like proton-proton colliders at LHC, because we give these particles very high energies, we collide them, and then we create very sort of exotic conditions after the collision, hoping that there are some new phases of matter that will show up that we could probe, and then eventually we see these some asymptotic particles that come out to the detectors and be able to analyze them and understand something about the underlying interactions. And this is how we discovered a standard model of particle physics itself, but we know that there is more. That's why we're continuing to build these colliders. And regarding the phases of matter, there are also things out there in terms of like astrophysical objects, like the interior of neutron stars, which is the densest form of matter that we know in the universe. And we still don't have a good idea of what the different phases of matter could be inside these neutron stars. Can we actually start from the underlying theory and make predictions for these really complicated quantum many-body systems that are often also very like dynamical, right? We're interested in kind of these real-time dynamics of these processes. So that's why we think that simulation is the way to go. We've made quite a bit of progress with classical computing, but unfortunately not quite a lot because these are very hard problems. So that's why we think quantum simulation can eventually, hopefully, enable this program. And we are going to use quantum entanglement and quantum coherence to be able to speed up these computations. But I'm going to mention something else. I'm going to mention that because now we have a different way of computing things, through quantum entanglement, we will have access to the states in the theory, which is something that we didn't have before. I'm not going to go into the detail of why not, but that means that we could also probe the quantum entanglement in these states as well, something that we couldn't do before. And maybe we learned something about the standard model itself, these like fundamental quantum field theories of nature, from the lens of quantum information and quantum entanglement. That's another objective for theoretical physics, to be really able to like fill up this hole in our knowledge, okay? All right, so let's talk about these collision processes. As I said, this is really the core of my talk. So we're going to collide high energy particles and then see what the outcome is. Can we classically simulate this, starting from the standard model of particle physics? Well, it turned out that to some extent we can, but I will tell you the limitations. We can do this, but only at low energies. There is a method that is developed called lattice gauge theory. So as I said, gauge theories are those theoretical frameworks that describe a standard model. Now, we can actually put them on a finite space-time so that we can make them amenable to simulation, essentially. And using that method, we can use our classical computers to do path integral Monte Carlo simulations, and which is very efficient, it turned out, to be able to answer some problems. The only thing is that we do these computations in imaginary time, Euclidean or imaginary time. The reason being that we want to do Monte Carlo sampling. If we don't turn our real time to imaginary time, then we can't really do important sampling unless Nathan and his students will tell us how to do this. using quantum computers. At the moment, with classical computers, we have to do this trick. We have to go to imaginary time to be able to do these computations efficiently. Anyway, so let me give you examples of how we have done with the classical computers in this problem, because I think I wouldn't do justice if I just say classical computers have been useless in giving us some answers. That's not true. In fact, from my past and current work, I have a few examples here of what we have achieved. We can start from a standard model quark and gluons, so really fundamental theory, and then do these computations using classical Monte Carlo path integral and look at things like the scattering at low energies of, say, two baryons. So baryons, you know, neutrons and protons, but they have also partners that are more estranged, like estranged pi primes and other objects. So they look like protons and neutrons, but not quite. You can actually scatter them and look at the underlying interactions theoretically. You can deduce some sort of extended symmetries of the interactions, write down effective interactions with these systems, just based on these fundamental calculations that you can do. So that's very powerful. Why do we care about this problem? Because it's related to the problem of what's in the interior of neutron stars, it turned out. So I'm not going to talk about that connection, but that's related. We can look at even larger objects. We can look at a nucleus that has 2, 3, or 4 nucleons inside it. So these are like 4-body objects. But if you think about them, they're infinite body systems because there are all these quarks and gluons, quantum fields that are inside them. And we can simulate them. We can look at the response of an object like that to a dark matter candidate, just something that experiment would care about, okay? And ask the question of whether the response is the sum of the response of the neutrons and protons individually, or are there nuclear or correlated effects because it's a quantum many-body system. What else we can do? We can look at proton-proton fusion, which is a primary process in production of energy in sun and similar stars. Again, starting from the underlying quarks and gluons. So this is quite remarkable that we can do a process like this, weak interactions. We can even look at more exotic processes like neutrino-less double beta decay. If you've heard of that, that's something that we're building billion-dollar experiments to search for a process like this. And we would like to understand theoretically what is the cross-section that we should expect for something like this. And we've started to calculate something like that. In fact, just this month, we have the first paper on the results of this work. So we're quite making huge progress already in the classical side. So why do I care to solve these problems with quantum computers? Okay, so you may have guessed, unfortunately, we can't do high energy processes yet. All these processes that I talked about, they were very low energies. I would create only a few particles in the final stage. And that's why I can actually access information about real-time dynamics in these processes, because all of them are real-time processes. You might have asked, how do you access them if you're doing Euclidean Monte Carlo computations? Well, there is a trick. You have to develop a very complicated formalism to relate Euclidean and Minkowski amplitudes to be able to do that. Unfortunately, we don't have that formalism for general processes, particularly if you create many, many particles in the final state. This would be probably outside the scope of what classical computers can do. Unfortunately, a lot of particle colliders out there are running very high at very high energies, like LHC, or something that we call RHIC, Relativistic Heavy Ion Collider in Long Island, New York, in the US, and so many other colliders. Okay, so why do we have problems? There are mainly 2 issues. The first one being that really creating complicated initial states is very hard with these classical computers, just as it is hard with quantum computers, but I'm going to talk about that today. All right, so for example, we need to make, for example, gold ions. These are the ones that are being collided in the RHIC in the US. Or you have to create very high energy protons, and we're talking about TeV scale energies, right? How do you do that? The other problem, as I said, is that our classical computations are imaginary time Monte Carlo, and we don't have a direct access to real-time processes, okay? So that's the sort of really the motivation. Let me tell you why we can't make complicated initial state using the current methods, just to give you a sort of a sense of the classical intractability of these problems. If you're a computer scientist, you might in your head ask, like, are these really classically intractable, right? So I have to give you some sense of what I'm talking about. So let's say that you want to simulate from QCD first principle, and by QCD, I mean the theory of a strong force in the standard model, the theory of quark and gluons. That's really the hard part of the simulations. If you want to start simulate an atomic nucleus that is pretty big, using quark and gluon degrees of freedom, the first problem that you realize is that these states are very complex if I write them in terms of the quark degrees of freedom. If you're interested in understanding how the system evolves, you have to calculate correlation functions between different space-time points. And then that means sort of a factorially growing number of possibilities for the quarks in your object to sort of propagate in the space and time. And so that's pretty bad. I want to give you a sense, if you have like an atomic nucleus that has 200 nucleons in it, you get something of the order of 10 to the 400 possibilities. So forget about it. You can't really fit it in the current computations.
Are all of those possibilities equally important?
There are some algorithms that will allow you to use the sort of symmetries and quantum numbers to bring this down, but it's still, it's not gonna work. So far we have algorithms that can give you silicon, which is I think 32 nucleons, but that's it. That's so far the limit. The other problem is that in these Euclidean time path integral Monte Carlo computations, we deal with a severe signal to noise problem. It's very similar to a sine problem, if you heard of the sine problem, meaning that our signal to noise ratio in these correlation functions drops exponentially fast as a function of the number of nucleons that we put in the system and a bunch of other factors. So we have another exponential problem here. So if you're trying to get the mass or the spectrum of these nuclei using these computations, then you have to have exponentially large sample sizes to be able to really resolve the signal from the noise. And there's some interesting physics behind it, but I'm not going to go into that. And then finally, we have sort of a resolution problem, because if I have a large atomic nucleus, the excitation gaps are going to become smaller and smaller compared to the ground state. This is sort of a picture that I have here from two random nuclei. I think it's radon and radium. And these are experimental measurements. And you see, like, these peaks are very close to each other. And we're talking about hundreds of kilo electron volts of difference between excitation gaps. And the mass of these objects is of the order of hundreds of giga electron volts. So we're talking about orders of magnitude difference between ground state and sort of the next excitation. We have to have that much resolution. It's not realistic. Forget about it. We're not going to be able to resolve that, particularly given that we have the exponential signal to noise problem and everything else. Okay, so we are not planning to do an atomic nuclei on a classical computer, starting from the quark and gluon degrees of freedom. There are other methods they can do that are more effective, but they're not really first principle. But at the moment, we're limited by this. The second problem, as I said, is real-time dynamics. As I said, we do path integral Monte Carlo. So we have a weight, which is e to the I times the action of the theory. And we go to Euclidean time so that we don't have to deal with this oscillatory sign. But if we wanted to real-time dynamics, we can't do that. We have to really deal with this oscillatory sign. And then we have to sample using a highly oscillatory function. And therefore, we have to have like exponential sample size to be able to resolve any signal from this computations. So that's the sort of the problem. So that means that we don't have really access to real-time dynamics after these collision processes. We can't think about things like thermalization and hadronization and so on and so forth, which are very important open questions in the current time particle and nuclear physics. Okay, what is the mechanism of thermalization, hadronization, equilibration, starting from the standard model in these processes, and a bunch of other observables that are real time and are important for our program. We don't have access to them. Okay, so this is really sort of the reason for seeking for other alternatives. So that's why we're here. again, as a summary, we're going to talk about how to go from theories of the standard model to complex processes like high-energy collision of particles in particle colliders. And we're going to use quantum technologies and quantum simulation computation to allow that program. Okay. Any questions so far? Okay. All right. So how do we do then a scattering using a quantum computer? Well, there was this very nice paper that came out already more than 10 years ago. 12 years ago, yes, by Jordan, Lee, and Preskill, that set this stage for how to do a scattering process in quantum field theories. Again, quantum field theories are the underlying theories of the standard model. So they looked at one particular field theory, a scalar field theory, and then they asked the question, if I want to set up the problem to do a scattering in quantum computer, how do you do that? And that process is very similar to what you have probably seen in your, if you're a physicist, quantum field theory textbook. It's called S-matrix evaluation or a scattering matrix evaluation. You have to then start with your initial particles, but you have to start from sort of wave packets of those particles. A wave packet is an object that allows you to actually move these particles towards each other. If they were like plane waves, then you don't have the sort of this notion of locality and the movement to put into these particles. So you have particle excitations, then you have to give them some dispersion so that you can actually move towards each other. So in the far past, they're far away from each other, they move into each other, and then they start to interact. And you can turn on these interactions adiabatically or in some other ways, but you have to make sure that you start from something that is non-interacting, and then it becomes interacting with the Hamiltonian of the system, it evolves, it collides. And then after the collision, you have the option of either observing what happened right after the collisions or far away. Unfortunately, if I do sort of a collider experiment, it's usually very hard to probe what happens right after the collision, because we are talking about femtoseconds of the experiments, like right after the collision. What are those phases that get created, and all of a sudden it thermalizes and becomes like these hadrons in the detector? It happens so quickly, and it's very hard to actually put the probes in the experiment right after these collisions happen, because we're talking about like femtoseconds of processes, right? But in quantum simulators, in principle, we have access to the wave function of the system at any time if we want. We can do measurements right here, and far away, just as we do with a particle collider. So that's sort of the power of a quantum simulation, okay? All right, so now that we know the procedure, let's try to think about how to build these scattering experiments concretely in our quantum simulators or quantum computers. So as I said, there's going to be two parts. In part one, I tell you that you can already do things like this in a spin systems. And then in part two, which is like part three, I'm going to tell you how to start doing these kind of things for confined excitations and gauge theories using universal quantum computers. Okay. All right, so let's talk about this part. The outline of this part is the following. I'm going to introduce a spin model that has confinement, which is a really interesting feature in a standard model or the theory of a strong force, would give us these composite low energy objects like these nuclei and hadrons and neutrons and protons. And we would like to have some notion of this confinement in composite objects also in simpler spin systems. It turned out that you have, and I'm going to tell you what those excitations are. I'm going to tell you how we can prepare these wave packet states of these composite excitations. Then the full scattering process, I'll talk about that. And then eventually you will see that in this same model, we can have very interesting processes, both elastic and inelastic processes, where you can create very non-trivial objects in the final states, in these high energy collisions. Okay. All right, so let's talk about the model. Let's just start from the top. We have the Ising model. Everybody is familiar with Ising model, right? You have a spin-spin interactions, and you can have a longitudinal magnetic field as well, sitting here. And this JIJ coupling between your spins could be general. It could be say, power law decay or exponential decay. And we look at both cases because it turned out that each of these cases would result in different scattering phenomenology. So that's interesting. So now, if this was the Hamiltonian, what is the spectrum that we would expect at low energies? Well, the vacuum is going to be all a spin-off. If I assume that HX and J0 are both positive, then the lowest energy configuration is all a spin-off, obviously. Now, it turned out that you can have another excitation in the system where you have actually all a spin-up and all a spin-down. We call these the kinks, or everybody calls these objects kinks. So the kink is actually a domain wall between the spins that are all up and all down. Okay, so the kink actually connects two sort of vacua. If HX was equal to 0, you had two degenerate vacua, right? All a spin down, all a spin up. Then this is really sort of connecting two of these vacua. But if HX is greater than 0, then there's only one single vacuum. Okay, now the interesting part is that you can have two of these domain walls and make things that are bound mesons, it turned out. And I tell you what that means. So what is this object? You have a domain wall here and another one here, and therefore there's one spin that is flipped in between. And we call this a length L equal to 1 meson. So meson is a kink, anti-kink bounded state in this object. You can also have like configurations where these things are not bound. You can have two kinks, but they're not bound depending on the model and so on. So these are the kind of objects that I'm going to deal with. So now you may ask, why do I say that these are bounds as opposed to being unbound? Well, it depends really on the potential. You can look at the potential between the two kinks at distance L. And like that would be this object. You can get it easily from this. This is just a constant and so on. And then you just plot it for different interaction, spin-to-spin interactions. And you see that for some of these interactions, the potential really grows unboundedly as a function of the distance. So what does that mean? As you take these objects apart, these two kinks apart, the potential energy in the system gets larger and larger. It's just like the spring notion, right? So that's why we have this confinement in the system. So then you can actually look at what range of the alpha parameters and the power law interactions and the beta parameters would give you sort of interactions that are unbounded, like confining. But in some cases, you could also have the interaction that would like to saturate. So if like in this case, you can have just the bound excitations in the low energy, everything bounds. But in these cases where things saturate, then you can have a mixture of bound and unbound kinks in the system. That's also very interesting. In fact, we see very interesting phenomenology here as well. Okay. So now that we understand these excitations, you may ask, well, that Hamiltonian was very trivial. It's all X. So it's like diagonalizable. Why do I care about this dynamic? Well, it turned out that I want to actually turn on something non-trivial. I want to add a transverse magnetic field to the system. And you're going to do this adiabatically such that you have still this notion of bound and unbound kinks. So you have the same low energy excitations in the H0 theory, and then you try to keep them and then sort of adiabatically evolve and then get the interacting kinks and bound states of the kinks. Okay, so the same story, you have these objects. The only difference is that now, because of this non-trivial term, these excitations would have a non-trivial dispersion, meaning that they can actually gain some kinetic energy and they can move, which is something that we want. So this is like a plot for the power law theory for different values of this HZ. So the larger it is, the more dispersion you get, the more kinetic energy you get. And these are the two mesons in the system. It turned out the low-lying states in the theory are two mesons, this guy and this guy. And the larger the Z field is, the larger dispersion you get. So for example, if I want to have a particle with momentum pi half and minus pi half to sort of work towards each other, I can, because I have this sort of velocity, the momentum dependent velocity now in the system. If Z would have been 0, you had like a flat band. So they could have momentum, but they wouldn't have any velocity. So I can't really do a scattering experiment with them. So that's why I introduced this factor. Okay. All right. So now we have excitations that can move. And are these real? Can we actually observe them in experiment? This is an experiment, which is an analog quantum simulation experiment in trapped ion systems, because we can have these long-range spin-spin interactions in an analog fashion in experiment. So they actually looked at systems as large as 40-something ions or spins, and they were able to look at the dynamics. So what they did is, starting from some initial state that was trivial, they then turned on this full Hamiltonian in the system, and then they were able to then look at different initial states, and then how in the quench dynamics they oscillate. And using the frequency of these oscillations, you actually get the energy gaps between the first excitations on the ground state and the second excitation and the first excitation, things like that. So like this is like reading the spectrum from dynamics, which is very interesting. And then they get these energies as a function of the distance between these kinks. And it actually grows and it's consistent with the theory. So you actually have sort of these confining force in this spin system. So this is being observed. So that means that they are ready, hopefully, to do the next stage that we're proposing, which is how to go beyond a simple quench experiment, make something that is more non-trivial as an initial state. In this case, these bound excitations of the kinks that are moving, and we are going to make a wave packet out of them. Okay, so this is how we propose to do that. So I want 2 wave packets of these excitations. Let's say one on the left and one on the right. And then I need a procedure to prepare them independently. I could do it sequentially or in parallel. In principle, both of these are possible. How do I do that? On either side of the chain, I start from the vacuum of the H0 theory, which was all up. In this theory, it's very easy to create these kink excitations and bound excitations. I just showed you that you just like flip the spins in this theory, essentially. So that's very easy. So that's what we do, but we do it in a very coherent way so that at the same time, we can imprint the wave packet profile into this superposition of the spin ops at different places. This is how we get the wave packet. The wave packet profile is the Gaussian, the usual thing that everybody picks. It's centered around x naught. It has some momentum k naught, and it has some width in position, and therefore momentum space. Okay, so that's how it is done. And there are 2 protocols that can actually achieve that. I'll tell you very, very briefly about those. But this is kind of the idea that you can actually generate these superpositions in a form of a wave packet in the free theory. Now, the idea is to adiabatically turn on the Hz field, that H prime term, so that these excitations can start to move. And you want to do this slowly enough so that these bands become isolated, they don't run into each other. We have the notion of these particle excitations intact, but at the same time being able to actually have a non-trivial moving excitation. So that's what we do. And then that's the U of R is this unitary that can do the ramp for you. And it's simple. Question?
Yeah, I'm curious, is this scattering paradigm that you're taking a look at it, is it known to be BQP complete?
In a scalar field theory, it is.
Yeah, exactly, but here.
It is dynamic. Everything is dynamic. So I suppose there is quantum advantage. I don't think anyone has worked out that this is BQP complete, but everything here is like dynamics. So it is like
there's this older work that Andrew Childs put into science, like in 2013, that showed that Bose-Hubbard model in particular can be BQP complete using scattering experiments like this.
Oh, interesting.
So it'd be really interesting if there's some way that you could set up corresponding gadgets for your model in order to either show BQP completeness or, more interestingly, show a boson sampling like quantum advantage for these types of things.
Okay, good idea. Yeah. Okay. So we should talk to you and Andrew about this. All right. Okay. All right. So now we have our wave packets on left and right. You let them to evolve and come to each other and collide. And then you start to ramp down so that you get back to the eigenstates of the free theory, because then these are easy to measure. You just measure the magnetization of the spins, and then you can then have these far apart free hadronic wave packets so that you can build something like S matrix element. Okay, so this is really sort of the full procedure. It involves two ramps, which are easy for experiment, but importantly, it involves this wave packet generation for which we have protocols for. Okay, so let me see. Maybe I'll tell you about one of these protocols and not the other, because I'm running out of talk quickly. So one of these proposals is based on a blockade interactions in these spin systems. What is a blockade interactions? It essentially means that I have the H0 Hamiltonian, I introduce an H1, but H1 is an HZ, which is time dependent with some frequency. So it turned out that if you tune the frequency of your drive to be the same as the frequency of just one spin flip and no more, then you can suppress other spin flips in the system. As simple as that. So you get a resonant term that would flip one spin and create sort of these one meson objects out of the fully up state. And then this HZ that I introduced, well, no problem. Just set it to the parameters of your wave packet. And then you get your wave packet in one go. You just like evolve the system with this Hamiltonian for time pi over gamma. You get your wave packet. Does it work? It does. This is a result of a numerical simulation. This is for one wave packet. This is for two wave packets on 25 spins. And we get 98 plus fidelity for generating these wave packets with the parameters of the experiment, say a trapped ion experiment. Even the error that comes from these off-resonant terms, that seems to be sort of consistent with the infidelity that we see out of these numerical simulation. So this is sensible. We have another proposal for this. I'm not going to talk about the details of it. It's based on spin boson interactions in the systems, which you have. For example, in trapped ion systems, there are phonons and they can interact with the spins. So you can actually use the intrinsic phonon spin interactions, essentially using these phonons to be collectively exciting your spin in the system. And you do that in such a way to, at the same time, imprint the wave packet excitations in that. Again, okay? So again, we reach very high fidelity wave packet generations. This is sort of a result of generating a wave packet first on the left side of the chain and then end, and then start creating it on the right. At the end of the time, you have two wave packets that are far apart, and they move toward each other after we turn on this ramp. Okay? Great. So we haven't done the experiment yet. Hopefully our experimental friend would do that for us in the next few months. But at the moment, we have done some numerics to see what to expect. So it turned out that there's not much interesting things going on with the power law model. It turned out if you start from two wave packets, scatter them, you just get elastic scattering, it appears. Because essentially energetics are very limited. This is like your meson band. This is the next meson band. So if you collide two ground state mesons together, you have to give them very high energies to be able to like get to the next band. And that very high energy means that this HZ should be very high and would take us outside sort of this ferromagnetic phase of the theory, and we don't want to do that. What about the exponential model? This is another model that is doable, also in trapped ion systems and other platforms. Well, here you see more interesting things because the spectrum is much more complicated. Here you can have both the meson bound states and the free kinks. So remember, the kinks are like quarks and antiquarks. So you can have both in the low energy excitations. So now if I start from two mesons, which are these stars on these bands, their energy could be compensated by these 2 points or these 2 points or this point and this point or this and this. There's so many possibilities for generating different final states. But we don't know which one would get generated because it's a non-perturbative dynamical problem that we have to solve, which we did here. So you generate these wave packets, you let them evolve, you scatter them, you wait long enough after the next ramp, and then you kind of measure the final state to see how much of the initial state you see in the final state, how much of non-initial states you see in the final state. And this is what you see. You actually see the elastic channel, which go down as a function of this the transverse magnetic field. And then you see this inelastic channel, which turn out to be two free kinks to actually go up. So it's really interesting because it tells you that you start from a quark, antiquark, a quark, antiquark bound state. So there are 4 of them. They collide and somehow they become just a quark and antiquark with higher energy. So this is called a meson disintegration in the context of a standard model, something that we're really interested to see in QCD in real time. We see it sort of here in this spin system. Yes.
So based on the basic model, you know which JFR we should do?
Yes. So I think like we would be interested in something like this. We want to see inelastic scatterings. Yes. Well, no, but so the part that I'm going to skip, that's sort of a particle physics model that would give you also these kind of excitations. But no, like for spin systems, we don't have like these exponential things that have a correspondence in the gauge theory side. But in the gauge theory, we can also get these inelastic scatterings. Okay, so that's very simple. In experiment, you can actually detect them pretty easily. So even if you have errors that you're worried about, it turned out this is a very robust signature because you have the kinks, and the kink is like all the spins are all of a sudden like finally in opposite direction. So even if you have a few spin flips error, you can still have pretty high fidelity observation for these inelastic channels. And pretty high probability too, about 25%. So we're excited to actually observe them in experiment. Okay. All right, let me go to, I'll skip this, just saying that the sort of take-home message is that you can kind of start to learn about the physics of confinement and scattering already in spin systems. And these are the things that are suitable for analog quantum simulations. People are doing analog quantum simulations of hundreds of spins now. This is cool if you can actually do them. And this is not QCD experiments. It's not going to satisfy me, but it's going to give me some insight about the role of confinement in simpler theories, and maybe just giving like some prediction or insight for what could happen in QCD. Okay. Yes.
Great. What was the numeric that you did with the method?
Exact organization. This was just 25 spins. So, all right. All right, so I'll skip this part, which was an interesting model, Schwinger model. Nathan has worked on Schwinger model, but I'm going to skip that. Scattering in the Schwinger model. Now let me quickly talk about hadron. So how much time do I have? I don't know when we started.
Yeah.
Oh my gosh, so less than 10 minutes? Okay, so let me tell you quickly about how to do this in a digital universal quantum computers. And I'm going to talk about the gauge theory. This is a 1+1 dimensional gauge theory, and we're going to build wave packets using a digital scheme now. Okay, this is kind of the outline of the talk, because the talk, this part is going to be very short. I don't need to give an outline about that. So let's go straight to the mechanism. So remember I told you about Jordan-Lee-Preskill algorithm? So the idea there was that so here is the coupling, here is the energy. You start from low energy and low coupling, essentially free theory. You start from the ground state of the free theory or the vacuum state of the free theory. Here, it is easy to generate particle excitations and make your wave packets, as Jordan-Lee-Preskill developed the algorithm for, because it's a free theory and it's usually simpler to think about the excitations here. Then once you're here, you adiabatically turn on interactions, and then you get your interacting wave packets. Just this similar mechanism that I talked about for the spin systems. Okay, it turned out that that's the bottleneck. Really, adiabatic preparation of these wave packets is very time consuming, and that adds to the complexity of the algorithm. Can we avoid that? So this is what we did. We said, how if you start preparing the interacting vacuum of the theory, find a way to generate the excitations that look like wave packets in the interacting theory already, and get there. So we avoid adiabatic procedure. Okay, so let's see how we can do that. The interacting vacuum, there are so many different methods to kind of generate interacting vacuums. Start from your favorite, maybe it's not your favorite VQE, all the way to other procedures. Probably not adiabatic, because again, we want to avoid that aspect. But then the question is, what is this particle excitation ansatz that I can make wave packet of in the interacting theory? How do I build that? This is really the hard part, right? And particularly if you're in a theory where the low energy excitations of these composite bound objects, in Jordan-Lee Presskill, they weren't. In the scalar field theory, you have your fields, and the excitations of those fields are low energy degrees of freedom. You don't have to do much about it. So you can't really get them essentially out of adiabatic evolution, because it's just like a different object, okay? So that's why we thought that we should have a different strategy here for these composite objects. So here is the steps of the algorithms. We prepare the interacting ground state. We optimize a momentum creation operator for these excitations. I tell you what that operator is. That's really the core of the algorithm. Then we just assemble the wave packet components, and then we build a circuit for it. Okay. Should I skip the theory?
Probably.
Okay. All right. So let's tell you about the ansatz for wave packet excitations in the interacting theory. The colors don't show up, which is very important to show up. Interesting. Can you see this?
Oh.
All right. So there's supposed to be Gaussian wave function all the way up there.
Yeah.
And then a Gaussian wave function over here. Okay. So there are like two Gaussians. One Gaussian is really for the entire meson object, this bound state. Okay. Because this is the object that is moving. So you want the wave packet for this. But each of these interior quarks and anti-quarks inside your mesons, what about those? What is the like wave function associated with those? These are bound states. They are really complicated. If we knew their wave function, we would have already solved the theory, right? So then here it comes a very interesting ansatz that we got inspired by some tensor network work that came out last year, that maybe we should try this and kind of optimize it for what we have in mind here. The idea is the following. Even the bound state ansatz itself looks like a Gaussian. Not only you have the ulterior Gaussian, you have an interior Gaussian. What is it? It tells you that you have quarks and antiquarks. If they're moving with the same momentum, then that's great. If they're moving with different momenta, you should penalize that, because it's a one-dimensional case. They're going to move away from each other. They're not going to form a bound state. Okay, so that's really the idea. There's some phase, and there's this Gaussian that would penalize the difference in the momentum of these particles. Okay, and there are only two parameters for each of the momentum vectors of these excitations. There are only two parameters. Then you have to optimize. Okay, does it work? Yes, it does. For the full parameter range of this model, we get very high fidelity ansatz out of this. It's surprising. And something that I didn't tell you about is that these quarks and anti-quarks in a gauge theory. Just to stop right now?
No.
Okay, so how many more minutes? Second.
If you wrap it up quickly, that would be great.
All right, let's stop 5 minutes.
Yeah, 5 minutes.
Okay, all right, sounds good. I think I can manage. Yes, definitely. The difference between this model and the spin model is that we have gauge fields. Something that I didn't tell you in the theory slide. The quarks and antiquarks are not just sitting on their own. They are connected by the string of gauge links. So that's the part that we have to also build in the algorithm. So these objects that we have here, these U objects, are the gauge fields that are connecting the quarks and antiquarks. And we have to account for that. So our ansatz is the following. We have a bunch of these meson excitations, like they're next to each other. They can be far away. They can be as far as the lattice can go, okay, in principle. And then we have to have all of those in our ansatz, it turned out, which could make the algorithm costly, but polynomially costly. But it is what it is. This is gauge theory. We can't really ignore the fact that this is a gauge theory, okay? So again, we get very high fidelity ansatz for two types of gauge theories, U1 gauge theory, Z2 gauge theory, still in 1+1 dimension. For system sizes as large as 10 sites, which is 20 qubits, because that's what we could handle with our laptop. Now here's the algorithm. Ground state, you can do VQE. It turned out that for these systems, there are some very efficient ansatz for VQE, which looks like trotterization. With a very few parameters, we get essentially perfect fidelity for these system sizes that we look at. So we don't worry too much about it. And then now that you have the ground state circuit, for each of those K momentum excitations, you have to also optimize and find the parameters of your ansatz to get those excitations. Okay, those parameters optimized. You can perform another VQE. That's a nice part about this algorithm, because in each momentum sector, the excitations are the lowest energy excitations. And these ansatz would actually take you from the vacuum to that sector because of the quantum numbers. So you can actually implement another layer of VQE to do the optimizations again and again. Now, once you have optimized all these momentum vector excitations in all these momentum sectors, you put them together with the Gaussian profile, this ulterior Gaussian profile. So this is kind of that step. It's a Hermitian operator. It's not unitary, so you have to make it unitary using the Anshilo qubit trick. The Jordan-Lee Preskel also did, so no problem. There are some other technicalities that you can use the algorithm that we developed in another paper based on singular value decomposition to be able to diagonalize these off-diagonal matrices very efficiently on quantum computers. All that done, then you end up with the full algorithm for the full circuit. Again, I'm really skipping a lot of details here, okay? But the full thing is in the paper. You can
Have you worked out the asymptotic scaling of the algorithm?
Yeah, so I'll come back to it to the last slide. Not to the degree that you like, but some. Okay, because it's VQE, we can't really do.
But you can figure out the number of operations per VQE step.
Yes. So I'll show you that. The cool part is that we were able to implement this on a hardware. So we used the Quantonium quantum computer based on trapped ion technology, and we were able to do a 13-qubit operation with up to 300 entangling, 3 qubits with 300 entangling operations. And really, essentially, what we say, I'm not going to say what these things are, but really, sort of, you have to compare these blue points with the red points, and they're pretty much on top of each other. So there's a pretty good performance. Something to notice is that we see like the wave packet. This is like the density, fermion density, or the quark density as a function of the site. And then you see like this periodic kind of wave packet. So this is like a sharper wave packet. This is a wider wave packet. You can do all those things, which is really cool. Okay. And this is another slide. And really, I finish up by saying that we can actually avoid the costly adiabatic state preparation if we have good ansatz for what these bound excitations are. We can use VQE to optimize them, and then we can actually build the full wave packet out of these. These are kind of those asymptotics maybe that you're talking about as a function of the system size, not the errors or anything complicated like that yet. But really, sort of the algorithm scales polynomially. It's like n cubed in system size. It turned out that you don't actually need all these mesons that are far apart because you have finite correlation lengths in the system. It turned out that if you just keep one of them, which are the plots that I showed you, you get pretty high fidelity already. And that would be sort of a linear scaling with the system size for generating these wave packets. Something that really the last thing I'm going to say is that it is very important that as we try to do QCD or more complicated gauge theories of the standard model, like QCD wave packets, we need a lot more insight. Here, we could have guessed what these bound excitations could look like to be able to optimize them and so on. Maybe we should get insight from the classical lattice QCD simulations of these states and their properties, whatever the property is, whether we get it from experiment or classical simulation, and kind of build that knowledge in our ansatz for the wave function. Because really, the quantum advantage comes into the dynamics to really generate them and study the scattering process. If you have some information about the initial state, why not using it to be able to build these objects? This is really where we're going. Okay. And summary and outlook is really say the last thing, we started from the spin systems that are easy. We're building our way up to more complicated gauge theories, understanding what is the most efficient path to get these sort of initial states that are more complicated because we want to do scattering processes. And really the obvious outlook is that the goal is really a standard model or QCD physics. We need to keep increasing the complexity of our algorithms, the spatial dimensionality, and at the same time keep them feasible and scalable so that we can actually achieve the goal of this program. And many thanks to my collaborators, my former students, now a postdoc in Seattle at IQS, current student Changcheng Xie, and also some collaborators at the QIS AMO Frontiers, student Elizabeth Benedicts at the UMD, former student of Alexei Gorshkov, now a postdoc at U Chicago, Ron, and also my colleague Alexei Gorshkov, who's been collaborating me on some of these more sort of AMO related topics. Definitely the digital front, we're sort of due to these two students and former students, and many other collaborators on these projects. Thank you very much.
Thank you, Zohreh.